Make it full screen. The option full screen. Yeah, go to it. I think we're just going to maximize.
Resolution problem, right?
That's the positive.
Still with the projector, yeah.
The projector is only 480p.
Hello, good afternoon, everybody. So, as we know, so we will have an online session as announced earlier. So, Professor Peliti will be joining us. Hello, everybody.
Okay, so this is interrupting. YouTube streaming is on. YouTube streaming is interrupting with this.
So we will have an online session as announced earlier. So Professor Peliti will be joining us.
It does 30 seconds.
No. No. Oh, that's my YouTube just closed. Unmute. Where is YouTube open? Yeah, closed. It's closed.
Close that. Yeah?
No way. Oh, unmute.
Okay, so
Yeah, sorry about that. So we have a simultaneous YouTube streaming also. So there is we had to make some arrangement for asking questions because Professor Luca is joining over Zoom. So if you have questions, please raise your hands, and one of the organizers will give you a mic and ask you questions to the mic so that Professor Luca can give you. Okay, so that's only one thing. With that, we can start. So over to you, Professor Luca.
All right. So I'm really sorry not to be with you, but I hope I can do something to help even from so far away. So today I will just give an overview of what is stochastic thermodynamics about, provided that this thing, okay. Why are we interested in it, and what are the systems of interest to stochastic thermodynamics, and relating stochastic thermodynamics within the general field of statistical mechanics and of thermodynamics, of course. And in particular, there is a sector of stochastic thermodynamics that is a relevance of information on information thermodynamics. And I must say that I think that the stochastic thermodynamics is the right setting to discuss information thermodynamics. And of course, we are going to see what are the main results so far of stochastic thermodynamics. So this is just, it will be just a general overview of what this school is about. So let's start from a definition of stochastic thermodynamics. Stochastic thermodynamics is a thermodynamic theory for mesoscopic non-equilibrium physical systems interacting with equilibrium thermal or chemical reservoir. So we are going to look at this definition term by term. Let's start thermodynamics. So stochastic thermodynamics, as the name says it aims at driving correspondence between a mesoscopic stochastic dynamics of a system, of a small system, and macroscopic thermodynamics. Mesoscopic means that the systems that we are looking at are comparatively small, and typically the idea is that they have a typical energy differences of the order of kT, where kT is ambient temperature, whatever that is. So For example, there will be colloidal particles, macromolecules, so molecular machines and the sort of stuff. But the idea is that we are always looking at systems in which the correct energy scale for the dynamics is of the order of ambient temperature. One typically considers systems in non-equilibrium, out of equilibrium, and systems can be taken out of equilibrium by basically two general means that are not mutually exclusive. One possibility is that you have a system that, if it left alone, will be in equilibrium, and because its energy function depends on some parameters, but these parameters are accessible to manipulation from the outside. So you can, by changing the values of this parameter over time, the system is no more at equilibrium and will, so in this case, we speak of manipulated systems. The other possibility is a system that is in contact with different reservoirs. And in this case, so the reservoirs either of energy, for instance, a typical situation is the one in which you have a system which is in contact with two thermal reservoirs at different temperatures. In this case, the system may eventually reach a steady state, which is out of equilibrium, although its properties during the time do not change. You have a constant flux of something, maybe simply heat, but it can be also chemical, that is crossing it, going from one reservoir to the other. So just in saying this, we see that we are considering systems that are interacting with some thermal reservoirs, and they evolve according to stochastic dynamics. This is important. The fact that since the system is very small, the usual deterministic behavior of large thermodynamical systems does not apply. So we have a situation in which the state of the system changes randomly due to the interaction with the reservoir, due to the thermal fluctuations. So the system evolved according to stochastic dynamics, resulting from interaction with one or more thermal reservoirs represented by random noise. So we are not going to look too deeply in what the reservoirs are. We are considering them as just being systems that are at equilibrium all the time. So we say that we consider situations in which the thermal reservoirs relax very fast, thermal or chemical reservoirs, whatever, relax very fast, so that they can effectively considered always at equilibrium. And the main point is that we have a separation of time scale. So the reservoirs are fast as far as the interaction with the system is concerned, with respect to the intrinsic dynamic of the system you are interested in. So this separation of time scales is a key to the simplicity of stochastic thermodynamics. Of course, this is an idealization, and there is a debate on how to say be more concrete in this, instead of this very rough idealization. Now, so let's see the situation of stochastic thermodynamics with respect to usual statistical mechanics. So in statistical mechanics, we start from a microscopic description of the system at the fundamental level. So the typical situation is when you make a model of a gas or a fluid, starting from a description of the molecules that interact, say, via the Lennard-Jones potential, and then you use the machinery of statistical mechanics to obtain the macroscopic properties of this system, in particular the thermodynamical properties. So this is done in one step. but we have learned that in fact it pays to consider the possibility of using some intermediate step. For instance, the whole idea of the renormalization group lies on the fact that you can sort of average out small scale degrees of freedom to obtain an equivalent description of the long range or the larger scale degrees of freedom. So in some sense, this led to the consideration of putting an intermediate step from the microscopic to the macroscopic, and this is mesoscopic level. That is what the stochastic thermodynamics is about. Mesoscopic systems behave according to a stochastic dynamics. Stochastic dynamics is due to the fact that non-equilibrium systems require anyway a dynamical description because their states usually change in time. But since the systems are mesoscopic, are on small scale, the dynamics is non-deterministic, say is stochastic. But the stochastic dynamics itself cannot be an arbitrary dynamical law, because it is constrained by the fact that the system eventually is a statistical system that has to obey the requirements of equilibrium statistical mechanics. So the idea is that you are looking at a system which behaves according to some sort of dynamics, but these dynamics eventually must be compatible with what we know about thermodynamics. And the way this is done in stochastic thermodynamics is the fact that the quantities that are relevant to the balance of the quantities that are relevant to the thermodynamics are evaluated on the reservoirs, which by definition are considered to be perfect, ordinary thermodynamical systems which are always at equilibrium. So the exchange of energy and entropy are evaluated, all the balance is evaluated at the reservoirs. And then we are going to infer what happens on the system by using these balances. The idea is that the resulting identities do not explicitly involve the dynamics. And this is, you get some sort of universality, that is the universality of the thermodynamics. But I remind you that this is due to the fact that all the properties of the reservoirs are swept under the rug. Disclaimer, in all my lectures, I will only consider classical systems, and the reason is that there are, to me, it's not very clear how to define a number of concepts in a quantum version of the stochastic thermodynamics. Now, just to have an idea of what are the main results of stochastic thermodynamics, there is this. So the first thing is stochastic energetics. Stochastic energetics allows us to define quantities like heat, work, entropy for a mesoscopic system at the level of a single trajectory. So the system evolves according to a stochastic thermodynamics, and therefore, during the time, it will pass through a succession of states, and this defines a trajectory. These trajectories are, of course, different in different realization of the same process. And the idea is that for each realization, it is possible to evaluate heat, work, entropy, and other thermodynamical relevant quantities. Now, since we have quantities like, for instance, the entropy production that are stochastic, for random, they have a probability distribution. One of the results of the stochastic thermodynamics that stems from the property of being compatible with ordinary thermodynamics and some extra considerations is a number of fluctuation relations that constrain the distribution probability of these fluctuating quantities. And so one of the most famous one is this relation that relates the probability of a given entropy production during a certain time interval within a given setup to the probability of having in the same setup or say in the same setup, the probability of having the opposite value of the entropy production. So the ratio of these two probabilities is equal to the exponential of the entropy production in units of the Boltzmann constant. So this is just one kind of the fluctuation relations. And from these fluctuation relations, you can get a number of very interesting conclusions. One of the things is, for instance, that it is obvious from this, the shape of this relation, that there is a non-vanishing probability of having a negative entropy production in a mesoscopic system. What sometimes is called a fleeting violation of the second principle. Another class of results are related to thermodynamics of information. The idea is that the information must be encoded in a physical system, and the physical system can be mesoscopic, and therefore enters into the scope of stochastic thermodynamics. And the idea is that the information on a system contributes to the entropy balance. And out of that, we reach, for instance, a number of conclusions like the Landauer's principle. Landauer's principle says that if we have stored our information in some memory, then erasing this memory to set it in a standard state requires at least, for each bit of memory, requires kT times log2 of work. And this is a way of reconciling handling of information with the second principle. Moreover, there are a number of relations that that constrain, for instance, the average values of currents or the average values of entropy production, if you like, but more generally of all kinds of currents, to their fluctuations. So these are called the thermodynamic uncertainty relations because they are somehow similar to the uncertainty relation in quantum mechanics. But for instance, so we have a relation in which the variance of or the variance of a current over a certain interval of time divided by the square of the average of that current must be larger than the quantity that I express here, that is, say, 2 divided by the exponential of the total entropy production in units of KB, in units of the Boltzmann constants, -1. That means that if you want to have a precise value of the current over a certain time, the larger, say, the smaller value of the variance means a larger precision on the current requires a larger production of entropy. You have to dissipate more in order to keep a certain amount of precision when you have, in order to keeping the value of the current constant. Now, a case which is interesting is that this can be used to have bounds on the efficiency of molecular motors. So define it, for instance, you have a molecular motor that is pulling a cargo with a given force F at a certain speed V, then the efficiency of this motor is given by the work done, well, the power of the motor, that is a force times its speed, divided by the total energy dissipated, that is given by this work, plus the temperature times the total entropy production rate of the system in a steady state. And out of this thermodynamic uncertainty relations, you can find that this efficiency must be smaller than the quantity like that. So in which you see that is 1 divided by 2 times the speed, kb times the temperature, divided by the precision of the velocity times the force. So this is the variance of the displacement, if you like. So, and the nice thing is that this kind of bound is related to quantities that are actually observable with a certain effort. Now, let's start from the definition of stochastic thermodynamics, stochastic dynamics. So we consider a system in which the states are denoted, the states of the system are denoted by X, and the energy of a state X is given by Ex as a function of a given parameter lambda. And the system, and we assume that these states are discrete, just to make the description simpler. Therefore, the system will evolve by staying in some state and then jumping from one state to another from time to time. These are called transitions. And we say that this transition happen with a rate that I denote by W, X prime to X. So notice.
Professor Peliti, can I ask a question?
Yeah, please.
So if you just go back one slide, when you were talking about these constraints on the efficiency of the molecular motors.
Okay, this one.
Yeah. So these, so these you're saying are applicable for molecular motors like kinesins and dyneins and myosin and so on, right?
Sorry, I don't hear well. So
these
can you repeat a very
applicable for molecular motors such as kinesin and myosin? These efficiencies.
Well, this is probably more like kinesin that I'm looking at.
So that's what I wanted to ask. So where is the structure of the molecule? Like what encodes the structure? So why kinesin and not, for example, myosin? So where is that information in this bound, in this relation?
No, this is on a steady state. So we assume that the system is on a steady state.
Okay.
Okay. And what sort of information? So I really hear very badly. So
am I audible now?
Pardon?
Is this better? Am I audible now?
Well, not much.
Not much. Okay. Is this clear? So I can.
Yeah, so the line just above that, the J stands for current, but current of what? I mean, probability currents, particle.
Okay, these are, for instance, J could be, in this case, J can be identified with V, that is the speed, and therefore the current is just a displacement per unit time. Or it could be, for instance, the rate by which a chemical is degraded. In the case of a molecular motor, you have, on the one hand, the motor moves along its substrate, and you have that ATP is degraded. So you have a current of ATP that goes into ADP. So this is another interpretation of J. Or one other possibility of current of interpreting it as a current is simply the entropy production itself. The entropy production rate is a current in this formula. So you have, even in this case, you can ask what is the fluctuations of the entropy production divided by the average entropy production square.
Sure.
Okay?
Okay, sure.
Okay, can we go?
Yes, please continue.
All right. Okay, now notice, so we say the transition from x prime to x, and we write it as with a jump rate in which x prime, so you see x prime is here, you go from right to left. This simplifies a great deal. So just keep in mind that this convention, and that in all what follows. So the state that you start from is on the right, and then the state that you go in is on the left. Now, the energy depends on some parameter lambda, and therefore also the jump rate will depend on this parameter. And once you are given the rate, the jump rate, you can write down equation for the occupation probability of a given state at time t. This equation is called the master equation for some historical reasons, and is like that. The derivative of this probability of staying in state x at time t is given by the sum of all different other states of two terms. One term describes the inflow probability. That is, you have a probability p of x prime of being, say, in state x prime, multiplied by the rate of jumping from state x prime to x. So this is going to increase the probability of staying in state x. On the other hand, from state x, you can move out to different state. So for each you have to subtract the probability, the rate by which this system staying in state x with probability px jumps to the state x prime. And this is called the outflow, and it's this term here. Now, the idea is that if you have a probability, if you just have a system that is described, that is can reach, well, let's put it this way. If you keep the parameters lambda of this system constant, and you only are in contact with a single thermal reservoir, then if lambda is constant, starting from an arbitrary probability distribution time t0, you eventually reach the equilibrium distribution, P of equilibrium of lambda. So this is just a usual situation in which we are considering a system in contact with a single heat reservoir, and the system eventually reaches equilibrium. Now, in order to reach equilibrium, the dynamics must satisfy a number of conditions. And so the condition is called the detailed balance condition. It tells you that for each allowed jump, say from x prime to x, first of all, the reverse jump from x to x prime must be possible, must happen with a non-vanishing probability, with a non-vanishing rate. Second, that the ratio of the jump rate from x prime to x divided by the rate of the jump rate from x to x prime must be equal to the ratio of the equilibrium probability of state x divided by the equilibrium probability of state x prime. And by the, since this equilibrium probability is given by the Boltzmann distribution, this is given by the exponential of the difference of the energies of the two states you're looking at divided by kT. So if you look at this quantity here, you see that this is the energy of the system in the state x prime where it started from. Say we're looking, say, identify x prime times x. So we're looking at this W here, and we see we start from x prime and we go to x, and this is the difference of the energy of the system from the initial state to the state after the jump. And this energy must be provided by the entropy, by the reservoir, thermal reservoir the system is in contact with. So we can write this. So what you have is that this quantity here is in fact the heat that the entropy, the thermal reservoir has received as the system jumps from x prime to x. It goes from x prime to x, and this heat must go to the thermal reservoir. And this is, of course, is a heat stochastic. It depends only on, it depends on the jump. Now, if this condition is satisfied, then at equilibrium, the rate by which, average rate by which you go from a state x to state x prime is exactly equal to the rate by which you jump from x prime to x. And therefore, there is no net probability current in the system. This describes a system which is connected to a single reservoir and is not manipulated. Once we're given this this situation, we can consider one possibility. So two possibilities: manipulation, that is, we are going to change in time the parameters lambda that describe the dynamics and therefore also the energy function. In this case, we say that lambda of t, considered as a function of t, is called the product, and it is denoted here, you see, by boldface. The other possibility is driving. The idea is that we connect the system to more than one reservoir, and in this case, the take balance can be violated. That is, this ratio is no more equal to this ratio of two, say, the values of two of the same function in the two different states. So there is no function that satisfies this condition, and therefore we have that the ratio that we are looking at is given by what we had before, but there is an extra contribution that comes from a different reservoir, for instance, and this contribution also goes eventually into the thermal reservoirs we're looking at, and so gives a contribution to the heat balance. If we write this in this way, the only possibility is that to have that the heat, say, this extra heat that is given to the system must be must change sign when you're looking at the reverse. This is just by definition of this relation. You have this parity relation. Now, what is a mesoscopic system? The idea is that we have a big reservoir with a larger number of particles that behaves deterministically. So if you are, it behaves according to ordinary thermodynamics. And then we have a system that is in contact with it, which is very small, the number of particles, say, order 1, or just a few, and therefore it's fluctuating. The dynamics of the reservoir is very fast, and the system is manipulated or is kept out of equilibrium. So we have that the reservoir is always at equilibrium, and the system has all its complex dynamics. And the idea is that the details of the reservoir system interaction are hidden under the carpet. We are not going to discuss this. And in fact, this is one of the most problematic points of stochastic thermodynamics. The idea is, where does the system stop? You can imagine that you are looking at the, say, macromolecule, which is manipulated. Well, the macromolecule is inside a solvent. Does only the macromolecule itself constitute the system, or we have to take into account, for instance, the solvent molecules that are in contact with it, and how far can we go and still keep some sort of validity of stochastic thermodynamics? These are things that I am not going to discuss, but you have to keep in mind that there is some problem in this setup. Okay, let's go to reservoirs. Reservoirs are thermodynamic equilibrium systems. So for an equilibrium system, we know that there is a relation between the energy and the entropy change, in the sense that if the energy of the reservoir changes by quantity delta E, then the entropy changes by quantity delta S, which is equal to delta E divided by T. So we have this relation. That is the usual relation equilibrium. Now, considering this relation, the usual situation is that the T is finite, and therefore delta S is well defined for each change of the energy. But we also consider in thermodynamics the possibility that, for instance, a thermal machine is used to pull up weight. So weight can be considered as a work reservoir. The idea of work reservoir is that you can change its energy without changing its entropy. So we don't assign entropy to a weight which is hanging somewhere. And in looking at this formula, we can say, well, this happens if T is infinity. And T infinity, in fact, goes quite well, because if you look at the Carnot principle, and you put a T infinity for the higher temperature reservoir, then what you get is whatever energy you take out of an infinite temperature reservoir becomes work immediately. The other possibility is that we want to change the entropy of the system without changing its energy. And in this case, we see that we're going to have information reservoirs, and information reservoirs are like systems at T equals 0 because of this relation. So information reservoir, we all know what they are. Oh, they are just hard disks and whatever. So they are systems in which you have microscopic degrees of freedom that in principle can be changed without expending energy. And now we see that although they can be spent without spending energy, changing the states of the system under certain conditions will lead to energy dissipation. Now, dynamics. Let's go back to the dynamics. We consider now a system that is manipulated. So we have discrete states. As time goes by, the energy of the states change according to a given protocol, and these are these curves that we see here. And the state of the system is denoted in blue, and we have that it follows for a certain time the energy of the state in which it is in this case, state 2, and then it jumps, say, to state 0, and then it keeps on, and then it jumps to state 3, and then keeps on. So what we have, the kinematics of such a system is given by trajectory, and the trajectory is given like that. At the time t0, the system is a state x0. Time t1 jumps to state t1. So between t0 and t1, the system is in the initial state, and then so on until we arrive at the last jump, like here, in which it jumps to state xn, and eventually at tf we stop looking at it. So the energy the energy is a function of a parameter lambda. Lambda changes as a function of time, as according to a protocol. The jump rates must satisfy, in this case, the detailed balance conditions. We are considering a system which is only manipulated, there is no driving. Now, the change of energy for a manipulated system from the beginning to the end, so from the end to the beginning, is given by the sum of the energy change during the jumps that we have seen is given by minus the heat that is provided. There is a sign convention. When the heat is released to the reservoir, we take it with a positive sign. When it is given to the system, it is we take it with a negative sign. This is the opposite convention with respect to ordinary thermodynamics, but it is the one which is universally adopted in stochastic thermodynamics.
I have a small question. So the system is always out of equilibrium at all times, right? The system is always out of equilibrium at all times, right?
No, you say this discussion can work also at if you have a system that eventually reaches equilibrium.
No, but as long as the system is not in equilibrium, how can we apply the detailed balance condition? I mean,
The detailed balance condition is a condition on the jump rates that defines the dynamics, and therefore you can take a system. So the system is given and its jump rates are given, so you have a well-defined dynamics, and this dynamics, if the system can eventually reach equilibrium, that means that the jump rates must satisfy the detailed balance condition.
okay, so the system will eventually reach equilibrium at some point in the future, so that's why we are.
If I stop manipulating and wait for some time, it reaches equilibrium.
No, but that's my question, right? We are constantly manipulating the system at all times according to these slides, right? So because you're constantly manipulating the system to not go into an equilibrium state, then how can we apply detailed balance? That's what I'm asking.
No, okay. If the system does not go to equilibrium state, we are in the driving situation that I have. If the system cannot go to the equilibrium state, we are in this case here, and the detailed balance must be violated by this extra term here.
Right. So if you're not manipulating or driving the system, only then we can apply detailed balance, right?
If there is no driving, then detailed balance must be satisfied. By definition, I split the systems into the ones which satisfy detailed balance and the ones which do not.
Sure.
And for the time being, I consider the ones which do satisfy detailed balance.
Okay.
Is that okay?
Okay.
Okay. Okay, so the difference of energy is given by two terms. One is the heat received from the reservoir, see, due to the jumps, and the other one is the work done performed on the system. The work performed on the system, you see, every time the system is in state 2 and it changes its energy. So this energy changes because the parameter lambda is changing in time. Therefore, some work must be done to provide the system with this extra energy. And this is due to the influence of the manipulation. And so we can associate it with work. So now we have that the work done on the system is taken with a positive sign. The heat given to the system is given with a negative sign. So this is a sign convention. that is used everywhere in stochastic thermodynamics, and is exactly the opposite of ordinary thermodynamics. Now, we can generalize these definitions to the case of a driven system. In a driven system, there are two extra terms, one on the work that is given, so beyond the work done to change the value of the energy of the state that the system is in, we have an extra contribution that is due to this extra contribution that breaks the detailed balance in the ratio of the jump rates. And so it's given by this extra term here. And there is also an extra contribution that is appears in the definition of the stochastic heat that is exactly equal to this term, and they cancel out when you evaluate the energy balance. So if you take this into account, we find that you can write the difference of energy between the end and the beginning in a given trajectory. So you start from x0, you go to xf with a given trajectory that is denoted by boldface x, is given by the difference between the stochastic work that is defined here minus the stochastic heat. And so we have that this relation holds for each trajectory. So we are arrived to extend, say, the first law. We arrive at extending the first law to a system, mesoscopic system, trajectory by trajectory. I think that we can. So the point now is, what about the second law? And this is what I'm going to discuss in the next. I think that now we can stop for a few minutes. Just I need to stop anyway. All right.
Okay, sure. We can stop for maybe 5 minutes.
5 minutes. Yeah. Okay. Great.
Okay. Sure. Yeah.
That's it.
Can I ask you a question? So this is the same as what you were doing in the morning, but in the jump state formalism versus the continuous blending. So the physics. The non-conservative. But here, the both of the detail balance
All right.
Shall we start again?
Yep. Okay, great.
Okay.
Okay, so it's clear that we can ask a question, what about the second law? And in order to discuss the second law, we have to introduce the entropy. So we have to introduce the entropy for a fluctuating system. Now we start from the fact that there is a measure of the information content of a probability distribution that is a Shannon's entropy and has this expression. So it's given by minus the sum over all the states of the P log P, or the probability log probability. This quantity has the following properties. First of all, it's non-negative. It vanishes only if we have a certainty about the state the system is in. And if we evaluate the Shannon entropy for a system, say, for the product of two probabilities. So in this case, we have two independent variables, say, distributed according to different probability distribution, then it is simply additive. And now, and the last thing is that if we have R states and then the Shannon's entropy of any distribution over R states is less than the logarithm of the number of states. Now, this quantity appears already in statistical mechanics by Gibbs formula. The Gibbs formula tells you that at equilibrium, the entropy is given by the Boltzmann constant times the Shannon entropy of the equilibrium distribution. Now, if we look at this expression and take this into account, we find that the entropy at equilibrium is given by the average of a quantity Sx, which is given by minus the Boltzmann constant times the log of the equilibrium distribution. So this gives the idea of considering for a general probability distribution the fluctuating entropy given by this formula, but of course, say for an arbitrary px. Now, the point is that once we do that, it means that in order to evaluate the fluctuating entropy, we have to evaluate the probability distribution in whatever state, whatever non-equilibrium state the system is in. If we do that, then we are able to write down the law, the second law in stochastic thermodynamics. Let's start again from the detailed balance. So I remind you that the detailed balance has this expression where Q is the heat released to the reservoir, and therefore it is equal to the average, is equal to the change in the entropy of the reservoir when the system goes from x prime to x divided by the Boltzmann constant. So consider now a protocol. Let's start from this system, which is a purely driven system. So we have a protocol and we have a time-dependent jump rates. There is a trajectory, and we ask, what is the probability of the trajectory? Well, the probability of trajectory, this is, we have to do in, say, in the Semitic way, starting from the right and going towards the left. We start from a probability of staying in the initial state, x0 at time 0. And then we dwell in this state for a certain time interval, say from t0 to t1. Probability of remaining in the state during this time interval is given by exponential of the integral of this escape rate. And the escape rate is the probability of jumping from a state to any different state. So it is given by the sum over all different states, different from the one we're looking at, of the jump probability from our state x to this different state x prime. So this is a probability of a dwell during the interval from t0 to t1, and say, and off you go, for instance, t1 to t2, tn minus 1 to tn. And then, of course, we have the probability of jumping in a short time interval of duration dt1 from, say, x0 to x1, and then, then from x1 to x2 and so on, and eventually, say, from xn minus 1 to xn. So we have sandwiches of dwell, jump, so on, dwell, jump, and the last is the probability of dwelling in the final state since the final jump to the final point in which we are monitoring the system. So now we have the probability of the trajectory, and we look at the reverse path. So we consider a path which follows the same states and has the same well durations, but starting from the final state and going to the initial state with all the jumps done in reverse. So in this case, this is the reverse trajectory with respect to the one we're looking at. We are going from, say, the reverse initial time is t hat 0. The reverse path is x hat, and the t hat is given by t0, say t hat is given by t0 plus final time minus t. X hat is equal to x of time hat of t hat, and the reverse protocol is lambda hat is given by lambda of t hat. So t hat goes from tf to t0, but we call it t hat 0 to t hat f. And you see all the jumps are done in the reverse. So we can just use the same formula to evaluate the probability of the reverse trajectory with the reverse protocol. And so this is given, say, the formula is the same. We start from probability of the x hat 0, which is the final state, a final time, if you like. And then we have the first dwell that corresponds to the last dwell in the, and then we go on. And so we have the same expression. Now we consider the ratio of the two probability of the forward trajectory with the forward protocol lambda divided by the probability of the reverse trajectory with the reverse protocol lambda hat. And here we have a big simplification. It's due to the fact that the factors of the dwell here, each of them correspond to a dwell in the same state for the same duration. And the value of the values of the jump rates during this interval are the same, because we are looking at the value, say, of the jump rate from x to any other one during the dwell in this reverse interval are the same. So we are looking, let's look here. So during this interval here, the probability of jumping to any other state is the same as we had in the forward trajectory, because they correspond. The things that are changing is the fact that the jump go in the opposite direction, but otherwise they're exactly the same. So the contributions of the dwells cancel out, and we are left with the contributions only of the jumps. Now, the contributions of the jumps, so we can use the detailed balance condition to express them in terms of the heat released to the reservoir. But we have the initial condition. The initial condition in the forward trajectory was given by the probability of staying in the initial state x0 at times t0. But the probability of this is the initial condition for the reverse trajectory, and this is the probability of being in the final state at the initial time of the trajectory. So this is some probability that the system has. And then we say one of the possibilities that we have is that say, well, okay, we just consider a situation in which this is the final the probability of being in a final state at the final time in the initial state. This is just a special case, but it's one of the most useful to consider. So if we do anyway, we have this contribution. In this contribution, we see that there is something that is the log of the minus the log of the final probability plus the log of the initial probability, and they are proportional to the fluctuating entropy in these two states. There is only this factor KB which is missing. So that means that these, okay, so let's for a moment forget about this contribution. If we look at the ratio of the conditional probabilities, say, of the trajectory starting from the corresponding initial state, these terms are not there, and therefore this ratio is equal to the exponential of the change in the entropy. So it's given by the exponential of the sum of the heat released to the reservoir in the during the trajectory, and therefore is equal to the exponential of the change of the entropy of the reservoir divided by the Boltzmann constant. And this contribution here, so you can interpret in terms of the fluctuating entropy, as we have discussed before, and therefore it corresponds to the change in the fluctuating entropy of the system between the initial and the final state. And out of this, if we take that if we take the probability of the so what we obtain is that in this case, with the choice of a probability of this choice p x hat 0 t 0 is equal to the probability of this final state in the final time in the forward trajectory, which is not necessary. But if we take this condition, then we have a detailed fluctuation theorem due to Seifert that it can be written in this way. The ratio of the probability of the trajectories, say forward with the forward manipulation protocol, divided by the backward, let's say reverse trajectory with the reverse manipulation protocol, is equal to the exponential of the change of entropy of the reservoir plus the change of entropy of the system divided by kT. So that is the total change of entropy, say, of the universe divided by kB. Now, from this, if we simply pull up this, say, we interpret this, we take the probability of the trajectory, we take this on the left-hand side, we have this relation, and by taking the integral, since the Jacobian and going from one forward trajectory to the backward trajectory is 1, that you can check it very easily, we obtain that the average of minus the total entropy production divided by Kb is equal to the normalization integral of the probability of the reverse trajectory. And so it is equal to 1. And then by Jensen inequality that tells you that the average of the exponential of a function is always larger than the exponential of the average, we have that the average entropy production is larger than 0. And this looks like the second principle. Now we had in the first principle was true trajectory by trajectory, but now we see here that the second principle requires an average, so it is only true in the average. Now we are going to see a couple of examples of this. So this is experiment on, actually it's not exactly in the stochastic thermodynamics, but is sort of a very sophisticated analog simulation of stochastic thermodynamics. There's a defect center in a diamond, in which the system, say, can be in 4 states. The states go in 2 groups. So in each of group you have, so the 2 groups are labeled by 0 and 1, and within each group you have an excited state and the ground state at different levels, so that the fluorescence of the system has different colors. So here you have red and green. The jumps between excited state and ground state within each group are very fast, but the jumps between the different states, different groups, are quite slow. So what we have is that if we forget about the inner dynamics in these within a group, we have that the system can be either stay in zero state and fluoresce red, or be in 1 state fluorescent with a green fluorescence. So it is just a 2-state system. A 2-state system is always satisfies trivially detailed balance. And then one can imagine that to change the probability, the rate jump rate. So here we have the jump from the state 0 to state 1 is this one, and the jump from state 1 to state 0 is this one. And you can manipulate these jump rates, and then you have you have different. So you have a different probability. You can manipulate the probability. So in this case, this is, if you like, this light curve here is the protocol. You see, so the protocol is just a sinusoidal modulation of the jump rate, say from 0 to 1, and this dark line here is the probability, occupation probability of state 1, and it starts from a certain value and then eventually reaches some sort of, say, periodic state that is in phase with the protocol. In this plot here, we have the state. So this is a trajectory. This is the trajectory, say the system starts in 0, then it makes a very fast accretion to 1, goes back, up and down, up and down. So this is just state. What we see here is the fluctuating entropy. You see, the fluctuating entropy requires to evaluate minus log of the probability of the state in which the system is in. So here we have something that is minus log of the probability of state in state 0, because up to here it is in state 0. We see a discursion to state 1, then it goes back to 0, and then it goes to 1, and then so on. So this is the curve of the probability that is sort of follows the curve of the state, but is still modulated due to the fact that the probability of staying in each state is modulated. So you see all these modulation. Now, summing up, what we do is we start from 0, and then we ask what is the total entropy produced up to a certain time. So we just integrate this curve, and what we have is a curve like that. And what is quite interesting is that it goes up and down, and in fact you have even a region here in which it goes down for quite a long time. That means that in this sub-interval here, the total entropy production, in fact, is negative, and is quite large, because it's comparable to what it had gained up to that time. And so what we have is that there is a non-negligible probability that during, say, a certain interval of non-vanishing duration, the total entropy produced is negative. Here we see a system which is driven. So that one was, say, a model of a manipulated system. Here is a driven system. And this is, again, I cannot, it is a simulation that I have done. But it's just a myelin that is, say, by itself. It does not act on anything. It does not, and the only thing it does is that it's sitting there. If it catches an ATP molecule, it may degrade it and then release the phosphor and go to being bound to ADP, then release the ATP and go back to the empty state. So these are just the 4 states. What we have is that basically these states, say the transition between empty and ATP are satisfy detail balance. The transition between empty and ADP also satisfy detail balance. But there is one step which does not satisfy detail balance, and this is the one in which ATP is degraded into ADP plus P. That is, say, much more likely to go in this direction than in the reverse one. So what we have, so in this case, what you expect is that the system will settle to a steady state in which it will turn around on between these four states on average in this. In fact, what we have is that the system just dwells a long time in the, say, between these two states, and then from time to time jumps to another one. Here I don't see any reverse. Unfortunately, it is not very, here I was unluckily, I was not able to see a reverse, but from time to time it does a reverse, even with these values, realistic values of the parameters. Now we go to, well, just the beginning of information thermodynamics. So everybody knows the Maxwell demons. What did the Maxwell demon do? Well, it was the idea was a finite being, but with very sharp eyes, that was able to sit down on a barrier connecting two parts of the same system, isolated system. And in this system, so within this system, there were gas particles with different energies. And the idea is that the demon was able to see if a particle with higher energy was going, say, from left to right, and open the door for it, and otherwise close the door if there was a low energy particle coming in, or if there was a high energy particle going from right to left. So if the demon were able to act for a certain time, we would end up with a situation in which the cold particles would be on the left and hot particles would be on the right. And therefore, the entropy would have decreased from the initial state to the final state. So it means, so this was one of the arguments that led to the interpretation of entropy as a probabilistic quantity. To make the argument a bit sharper, Szilard considered a demon which worked in this way. You have a cylinder which contains a cylinder is in contact with a thermal reservoir at a temperature T and contains a single molecule. And at a certain point, the demon introduces a division in the container. And of course, the particle will stay on one side or the other. Once the demon then is able to identify the part where the particle is in and attach the wall to a weight, and then let the gas expand reversibly by moving this wall. So by the push of the particle on the wall moves it until it reaches, say, the other end of the container. And in doing this, it lifts the weight for a certain, it lifts the weight of a certain height. And when it's done this work, when it's done this job, then the weight is removed, the wall is removed, and we are back to the initial state. In this way, in principle, one is able to extract a kb log 2 of work out of a single thermal reservoir. Now, the Maxwell demon experiment to show that the entropy is related to the lack of knowledge of the system. If we are not able to know which particles are hot and which particles are cold, then we are not able to act on the system. Therefore, thermodynamics, usual thermodynamics applies. So Maxwell, Boltzmann, and Gibbs emphasized the link between thermodynamic entropy and the disorder of the physical system. And Szilard demonstrated that information in the system can be used to apparently violate a second law. And how do you say, how can you reconcile this, say, for instance, Szilard demon or the working of a Maxwell demon The idea is that the information of the system must be taken into account in the entropy balance. And this is what we are going to see better probably tomorrow. And the idea, and each entropies are the contribution of the entropies of the information are of the order of kb per degree of freedom. For mesoscopic system, the fact is that the differences in energy are of the order of kBt, and the difference of the entropy are of the order of kb. So we have to take into account the information because they are in the same ballpark. So let's put this in the thing in say, more graphical way. We have a system. The system can be in contact with different reservoirs. We all know and love the heat reservoirs, and so in the heat reservoirs can exchange both entropy and both energy and entropy with the system, with different, say, different efficacy, if you like. But we also have considered work reservoirs. Work reservoirs are able to exchange energy with the system without changing entropy. And information reservoirs are exchanging entropy without exchanging energy. If we look at Carnot engine, what is doing Carnot engine? Well, it extracts heat and entropy from high energy reservoir. It releases some energy and the same amount of entropy in the ideal case to the lower temperature heat reservoir, so it's cold reservoir, and it releases a certain amount of the balance of the energy to a work reservoir, and there is no connection. There is no connection to an information reservoir. In a refrigerator, Carnot refrigerator, the heat goes from the cold to the warm, and it needs the influx of energy from the work reservoir. A Maxwell demon is, what is a Maxwell demon? It takes energy and entropy from the cold reservoir, eventually releases energy and entropy to the warm reservoir. But because this entropy, there is, in order to have balance of entropy, you need to have that a certain amount of entropy goes to an information reservoir. The idea is that the demon, every time it does something, performs a measurement, and therefore its state changes. And the change of the demon state, say, it starts, say, from a blank slate, but eventually it has all the, say, takes up notes of which molecule is what. And that this sort of increases the entropy of its inner state. This is clearer probably with the Szilard demon. What is Szilard demon doing? It's taking heat from the warm reservoir and it transforms it into work. Okay, there is no other reservoir. But here it takes some entropy, does not release entropy to the work reservoir because the work reservoir cannot have any entropy. And therefore some entropy goes to the information reservoir, which is simply the memory of the demon itself. But in order to go back really to the initial state, the demon has to erase his memory. And in order to erase the memory, what you have is that you have to remove this amount of entropy from the information reservoir. You cannot do that without, say, you have to give some work to the system in order, and then move this in order to release this entropy to the heat reservoir. And you see that in this way, what you're doing is exactly the reverse action of what the Szilard demon was doing. So the problem is that, so this is entropy reservoir, let's say. The entropy reservoir is a thermodynamical system that handles information. It is that it must possess several states, a computational state, that are non-equilibrium but long-lived. No, we all know that. Say, really, if you let a system, well, all the information handling, if you heat up, for instance, a magnetic tape, you lose the entropy that is inside. So they are in non-equilibrium, but stay in non-linear, and therefore they are necessarily non-ergodic. Means that the dynamics must be such that they remain in the same computational state for a long time. And so the computational state corresponds to ergodic components of the space of the system, and they are macroscopic or mesoscopic states, say, with its internal energy, entropy, and so on. But we are only looking at the information degree of freedom of this state. And so we are going to discuss in tomorrow, I guess. So I think I can finish here. If there are any, I hope there are a few questions. Okay.
So, questions?
Oh, okay. So Amitabha, you asked a long time. You asked a question. So on the uncertainty relations.
Luca, can you read the question?
Yeah. Say, okay. Say, the idea is that, well, myosin, surely you can use them on myosin. The fact is myosin usually has a comparatively short time in which it is in a steady state. So on kinesin, it is easier to see the steady state. It's just, I mean, but really, say, myosin works exactly in the same way, only that it lasts shorter. The other thing is that the myosin is highly cooperative, and that complicates the thing. You have, say, there are sort of bunches of myosin working together.
Thank you. Thank you, Luca.
Thank you for your presentation. I have a question. The theorem behind the photonic demon of Maxwell is the same. They're doing something about it. I wanted to know if you know.
The theory behind Maxwell and Szilard demons, well, the setup is different. You see, in Maxwell demon, you have two heat reservoirs, because you are separating the left and right hand side of the container, and the demon is moving particles from one side to the other. And the Szilard reservoir, there is only one reservoir, but say the problem with the demon itself is the fact that it handles information, and therefore its state changes remains the same.
Okay, but in photonic demon of Maxwell demon photonic that they're using, there's nothing like info, or is there?
Photonic demon.
I know that
Well,
recently they have made something like Maxwell demons photonic usage.
Oh no, okay, but there is a handling. There is a handling procedure. So
Okay.
this is the information.
Okay, thank you.
It's a feedback. You have to use a feedback to do it. And if you have feedback, it means that some information must be stored. As soon as you store the information, then you have the problem. because you need to have an information reservoir. You need to have a memory that keeps that information, and to erase that information need work. Usually you don't care because the system is, say, at room temperature, and it will erase it anyway. But in principle, if you are sticking to the situation, to a system that is isolated, then you need some work to erase your information.
Hello, Luca, can you hear me?
Yeah.
So my question is, even earlier when you derived this Crookes relation, this microscopic reversibility, so is there any way to include non-Markovian like memory dynamics to show so in case of dynamics with the memory, the microscopic reversibility conditions of the Crookes relations, are they true or validated or not?
Well, I have a philosophical problem with the non-Markovian dynamics, because in principle we say we all work with the ideas that the state of the universe, say at a given time, determines what happens later. Okay, so that means that whatever influences the future of our systems is contained in what the state of the system is here. And this means that say that the dynamics must be Markovian. If it is not Markovian, it's because you are forgetting a number of degrees of freedom, and you better look for which degrees of freedom would be relevant and put them explicitly in order to reach a Markovian description. So this is my idea. Of course, this is what I say. This is a philosophical attitude, and I don't know if you can set up the formalism in some conditions with the non-Markovian dynamics. I think that it will be quite difficult, and in this way, in a sense, you are going to complicate the things, because if you have a non-Markovian dynamics, that means that you have some information lurking in the recent history of your system that you have to take into account, and this is information that contributes to entropy.
So if there are no more questions, we will stop for now, and Professor Peliti, we will meet you again tomorrow.
All right, great.
We will continue with our tea break. Okay. Thank you.
Thank you. Thank you.